Okay, we're in section 40 of the notes. This is the section on volumes, and we're doing it by a cylindrical shell. So what's important is you paid attention during the lecture, you kind of understand this picture how it relates to a graph, and then understand that when you cut that shell, it folds in, you can fold that into a box. And basically we're doing is summing up a series of boxes using integration. So we'll go through some examples now. Again, part of the examples is going to be visualize the shell. These pictures over here were lifted from a book. I'm still going to draw a picture on the side to indicate what you need to be looking for when you draw these pictures. We'll set the integrals up and we'll do the integration, all right? I'll also do this one by the other method, which we use the disk method to do that as well. We'll get the same exact answer. And then of course, there'll be a chance to try on your own. And you want to try on your own. You want to try these problems on your own, all right? Independently. If you need help though, please feel free to come by during office hours and I'll be more than happy to help you. I'm going to switch to the whiteboard. Give me a moment to do so. Okay, you see my whiteboard? We'll do the first example. Again, I will look at their picture. I like their picture better than the picture I'm going to draw, but the bottom line is on exams doesn't mean we're going to give you a picture. All right, so if I were looking at this one over here and someone said, can you do that by cylindrical shells or by disk? I'd say, well, let me give it a try. I don't know if I can do it until I try. So what are you going to do over here? The first thing I recommend you do is just draw the picture of it. All right, so I'm going to try to draw the picture. You know what? My pencil seems to be running out of power here. Give me 1 second. I gotta see if I can get that to work there. All right, let me try again. Yep, there you go. So let's put this down. I'm going to draw a picture of this. I might as well use that line they got already drawn there, right? This is the x-axis. This is the y-axis. And they got a line y equals x. It's fairly easy to draw in. And they have another graph is y equals x squared. And that looks sort of like this over here, which I know has 2 points of intersection. And I do see the region now. I want to point out the region I'm seeing over here is the region in here. I'm seeing a region now. All right, let me put the points down for you. Fairly simple. It's 1, 1. And this point over here is 0, 0. Now, what are they going to do with this? They're going to rotate it about the y-axis. So they're rotating it like this. All right, about the y-axis. There's many ways to do the integration. It's going to be a volume problem. I'm going to say one way to do it is by a cylindrical shell. So what I'm going to do is I'm going to draw a rectangle here. You know, so I'm always drawing rectangles when I do this. And what I'm going to do with that rectangle is I'm going to rotate it. And if you rotate that rectangle about the y-axis, you would see this shell, a shell. I put this over here. And again, I'm not saying these are accurately drawn, but it's good enough for me. Then what do? We cut the shell. We cut it and then we fold it flat. And if you fold that flat, you can look sort of like this over here. Got a thickness to it. All right, so let's take a look at it. And you know, when I'm doing this over here, you know, I want to make sure that you know that this thing here, this base of this thing corresponds to a dx in the problem. So I'm going to say, if I'm going to do this integration, I'm going to go along the x-axis. All right, so the x's are going to go from 0. I'm going to put out what I mean by this. We're moving in this direction over here. And what are we doing? We're going from 0 up to 1. Then what do we got to do? Well, I know the differential's dx. All right, let me put out what I mean by that. This thickness over here is dx. Let me go back over here. This thickness here is dx. And what do I have to do over here to get the dimensions of the box? There's 3 dimensions to that. I got to do the height of it. And the height of it is going to be upper, which is the curve y equals x, minus the lower. Again, this is the upper, this is the lower. So the upper is y equals x, the lower is x squared. So let me write that down. So it's going to be y minus, y is equal to x, right? I didn't mean to say that. It's x minus, that's the upper curve, x squared. Remember, the upper curve is y equals x. The lower curve is y equals x squared. So the difference is x minus x squared. So I got that dimension. I'll put this over in the integration. Next thing I got to do is circumference. And what's the circumference? Well, this is the radius. This is the radius. And what does the radius correspond to? Just the x coordinate on the x-axis. So the circumference is going to be 2 pi the x coordinate along the x-axis. So I was going to put that down. And what do you get over here? Well, I got to do the integration. I'm going to put 2 pi down. Whoops, I forgot to put the x there. 2 pi. I'm going to multiply it. What do you get? X squared minus x cubed dx. A fairly easy integration to do. Let me do that. And again, we'll get an answer. We'll be able to check it with the key. That's going to be x cubed over 3 minus x4 over 4. Limits of integration would be 0 to 1. Let's do the evaluation. It's 2 pi. That would be 1/3 minus 1/4 minus 2 pi. What's nice about the lower limit, it evaluates to 0. Let's do our work. And what do you get over here? 2 pi. The common denominator is 12 over here. And you get 4 minus 3. That's 2 pi. And that would be 1/12, which can be pi over 6. And what's that going to be? Well, it's a volume. It's going to be cubic units. All right. Let's go to the next page and see how we did. Now, certainly I'm seeing that. I'm seeing the work over here. But they also said I could have done it by a disk method. By the way, this picture over here may be more helpful for you. I want to promote textbooks for you. Textbooks have much better pictures than I could ever draw. This picture here is taken directly from a textbook. It's a typical problem, right? Typical problem. All right, let's do the disk method. And the disk method, I want to point out, looking at a disk in this problem over here, I'm going to do really the same problem. I'm going to put it down by disk method now. Just give me 1 second to do so. This looks sort of like this. Get the points here, 0, 0, and this is going to be 1, 1. I'm going to use the disk method. I'm going to, put my rectangle in, something like this over here. And we're going to rotate it. We're going to rotate it like this. And someone says, why did you put the rectangle like that? Well, because I'm making a disk out of it. What I know about the disk is it's going to go along the y-axis. So I'm going to say that differential over here is dy. I like to do the differential first because it sets the tone of the problem. This is dy. We'll get the same answer, by the way. What are the y's going from? 0 to 1. If you do the disk, I want to do the big disk first, this one over here. All right. So that big disk, if I kind of drew a picture of it, the big disk would look like this. This would be the differential y. Now this would be r, the radius of it. So what's it going to be? Pi r squared. I'm doing the big disk. Now, what's this going to be? Well, it really corresponds to the x coordinate, the radius, right? So what is that curve? It's really y equals x squared, right? But I want to know what y is in terms of x. So in that quadrant, what is it going to be? Well, x would equal the root of y. So I'll write that down for you. That's the big disk. Now what I got to do? I got to subtract away the smaller disk. Let me push this on the side. Now I got to, I'm going to do, I'll get my eraser out. I'm going to erase this old business over here. We're done with that. Again, you may not done with that. All you got to do is rewind the tape when you watch it at your convenience. All right, let's take a look at that. I'm going to do the smaller disk. I'm going to point out what the smaller disk is for me. It's, let's take a look at that. Whoops, sorry about that. It's this guy right over here. I got to remove that part. All right. How do you do that? Well, it's still going to go from 0 to 1, pi r squared dy. Now, the smaller disk corresponds to that line. And what's the line going to be? Y equals x. So what's the radius over there? It really is x, but we need in terms of y, and x equals y. All right, let's do our integration. And again, we have to do that. It's going to be pi 0 to 1 y dy. We'll do that later. Minus pi 0 to 1 y squared dy. Let's be careful. We're going to get the same exact answer, by the way. Pi y squared over 2, 0 to 1 minus pi y cubed over 3, 0 to 1. Let's do our evaluations. What do you get? Pi over 2 times 1 minus 0. That one's done. Minus pi over 3. That's going to be 1 minus 0. What do you get over here? Pi over 2 minus pi over 3. Well, common number 6. That would be 3 minus 2, which is 1 pi. We get the same answer. They're cubic units, by the way. So both methods lead to the same answer. We wouldn't expect otherwise, by the way. Again, work is put down here for you. I know we didn't do much work. We've been spending much more time in the disc method. However, there are some homework assignments that you should work through. If you think you need more additional practice, what I would suggest you do is take a look at your book, right? Take a look at your book. What book are we talking about? Any calculus book, any calculus book. Now, if you look at a calculus book, they got tremendous number of examples for you to try out. Again, you may say to yourself, I don't need to practice more. I understand what you're doing, and that's fine. Just reinforce it with the homework giving. When you get to the exams, it should be relatively the same. I'm not going to say easy peasy lemon squeezy, but with practice, easy peasy lemon squeezy. Thank you for your attention. Again, if you need any help or assistance, please come by during office hours, and I'll be more than happy to help you.